In the demonstration today, I'm going to talk about an Internet of Things, an IoT demo, where we're managing a resource trading network. And in this demonstration, we're going to look at the IoT architecture and how we're communicating back and forth with the individual devices as we manage the trading network from a cloud-based server. My name is Martin Madsen. I have a PhD in experimental physics, and I have 16 years experience working with data of all shapes and sizes, including from taking data from sensors and predictive model building. So the scenario is a network allocation of resources, where imagine we have a collection of resources that are grouped together. For example, in the upper left-hand corner we have buses and electric charging stations and elevators and a power plant and vaccine dispensers all in one geographical location. But perhaps this isn't the best allocation of resources. Perhaps it would be better if we traded. For example, the medical devices and the vaccine dispensers might make more sense if they were together. And if we were to trade the dogs and the vaccine dispensers, the entire network would be better performing. So we're going to make a prediction that if we swap these items, then the network would have an improved group and the overall utility would be improved. So the design of this system is that we want to attach an IoT management to each one of these devices and then gather together information about where they are and in what group they are, and then make a prediction and then manage the trades. Who goes where and how do we improve the overall performance of our resources. Of course, some of the systems, some of the pieces of our network can't be traded. The power plants and the factory floors can't go anywhere. So we need to take into account that parts of our network are fixed resources. And so we need to know that. So the trade-offs that will come in this trading network. So we're going to consider that we can trade pieces back and forth. And on the downside, we have the resource mobility. Some things are easier to move than others. The cost of transport, of course, from one place to another, and how far these resources are moving. And the payoff is that if we move, we might have a better network. So what we're going to do is simulate this using a set of poker hands. So we're going to consider that we have poker tables at a variety of different locations, and that each table has a hand, and in each hand is a card, and each card becomes our equivalent IoT device. And we imagine that if we could swap cards between two hands, that each hand, or the overall net of all the hands in our network, would improve the quality of the hands, and the quality being measured by what's the likelihood of the hand winning. So we initially start with scoring hands. How do we know what quality each hand? And we develop a simple, straightforward scoring scale, anywhere from a scale of 0, that you don't have anything but a high card, all the way up to the royal flush, which we'll call a score of 9. We use the XGBoost machine learning algorithm to score the hands. We provide about 4 million hands of different shapes and sizes, anywhere from 5 to 7 cards, which covers basic poker as well as Texas Hold'em. And we train the model to make the prediction. Given a specific hand, can it predict the actual class of the hand? And the model does a pretty good job. It's better than 99% accuracy. And you can see the diagonal of their confusion matrix here is the vast majority of scores on every possible class, that the prediction and the actual agree very well with each other. We're going to put our hands in a simulated geography, and we're primarily going to use casinos in Las Vegas. So we've got 12 casinos in Las Vegas, and these are, of course, just simulated based on the geographical location, latitude and longitude. And we'll pick one casino in Atlantic City to simulate what would happen if we tried trading hands across country, which is a significantly higher transportation cost. And then each casino has 3 different poker rooms and 2 tables in each room and 2 hands at each table, which gives us a wide variety of combinations of hands to trading. The cards are going to be simulated as Windows 10 IoT Core devices, and they're running a Node.js script that takes care of the information about the hand, about each card. The cards themselves have 2 individual properties. They've got the transportation cost, the cost of moving each card, and so I'm simulating that as a parameter for each card. And then cards also have an occupation level. So if it's a very high number, for example, table cards that can't be traded, then the cards are not likely to be traded by our trading algorithm. The card simulation can do two different things with each card. It can change cards, so we can tell the device that we're dealing it a new card, and so it will change card properties, including the occupation level and the transportation cost. And then the other thing the card can do is it can move locations, so it can change its hand properties. What hand does it belong to? Where is the hand located at? Each simulated device connects then to our cloud-based server, and we're using the Microsoft Azure platform. And so our IoT architecture is a very simple architecture. We've got the IoT hub, which is the Azure-based communication hub for connecting to each device. And the IoT hub then will be connected to by two different web jobs. And part of what we're using with the IoT architecture is a lot of back-end systems and processes that take care of most of the maintenance of the IoT system for us. In particular, we're using what's known as a device twin. The device twin is a method of maintaining information about the properties of each device, and it's handled mostly by the back end. Each device twin has three different sets of identity properties to it. It has tags, which are just read-write from the back end, so we can keep track of what device twin is where. And then there's a set of properties, both desired and reported. And on the device app side, it can read the desired properties and then change its state based on the desired properties. And it can also read and write reported properties. This is coming basically from the app saying, this is what I'm currently doing. And on the back-end side, it can read the reported properties, and it can read and write the desired properties. And so this is how the server goes about changing the cards. It writes to the desired properties, which then the device receives those desired changes and then goes about making the changes desired. This is how it works. For example, imagine we have a device. It's a card and it's a king of clubs, and it's located at the Mirage Casino in Las Vegas. And it reports in to the server saying, this is who I am and this is where I'm at. And the server then establishes a twin that then mirrors what's going on with the reported properties. Then at some future point in time, the server says, we need to make a change here. For example, we need to change the card to an ace of hearts. That then gets reported back to the device as a desired change. The device then goes through the process of changing the card, whatever that might be, or in the case of moving, it would go through the process of getting itself into a state of moving, registering that it's shipping or changing, and then registering that it's done. So at a future point in time, the device then registers back that it's now reporting that it is the same as its server twin, and everybody's happy, and then the communication stops for the moment because nothing is changing. So going back to the IoT architecture, let's look at the web jobs. Now that we have a system where we can manage devices and we can use the device twins to make changes to their properties, we want to be able to do two different things with our architecture. We want to be able to deal cards, set up the system where we put the system in an initial state, and then we want to be able to execute our trading algorithm to optimize the resource allocation. Looking first at the card dealing, I'll walk through here the simulation and how this is working. What I've got are 11 different instances of the node simulator all running simultaneously. And so each one is representing a device that would be operating or running on Windows 10 IoT Core. So devices 1 through 10 are stacked together, device 11 is off to the side, and then the last piece is the server monitor, which is another node script which is watching the server and the status of each of the devices. So each of the devices are on and in the ready state when we send it from the Azure IoT portal, from the web app. We run that web job and send the move command and the deal command to each of the devices. And so all 11 cards right now are registering that they're moving and they're dealing as they move locations and change card state. And then all of them report as ready when the cards have arrived and have set themselves as their new state. So now in this configuration, we're ready to execute trades. We have two hands. It's a very simple trading algorithm. But with those two hands, we're going to see if we can trade cards and optimize the resource allocation. To do that, we call an Azure ML pre-trained algorithm that looks at the hands and then optimizes the resource. Now I have another web video that I'll link to in the description that describes this algorithm in detail, how it goes through and uses basically a trading network like the traveling salesman problem, and then anneals it to a state that's improved from, hopefully improved from the initial state, the initial configuration. Basically, the way it works is we swap hands, we try swapping hands, and ask, did that swap improve the situation? And if it did, we keep it, and if it didn't, we throw it away and try swapping a different set of hands. And then over time, the graph in the bottom shows that as we make the probability of swapping the cards, keeping a bad swap lower and lower over time, over the iteration, that the whole network improves and reaches a significantly better score, overall score, where that's the sum of all the possible hand classes. And then at that point in time, we know what we've traded, and then we send the command out back to the network, and the devices that make the change. So this is our demonstration, our setup simulation, where we have the two hands. One of the hand is marked by the stars in the upper right hand corner of the card, and the other hand is marked by the pluses. This is our starting situation. One of the hands doesn't have anything at all, it just has a high card of an ace. The other hand has a pair of sevens, which is not a great hand, but it's something at least. And then when we run the trading network, it then comes back and says we want to trade 6 of the cards, 3 pairs. And then it sends the command out to the card saying we need to move to a new hand. And then the resultant hand is that we end up with 3 of a kind in the star hand. We have 3 sevens. And in the other hand, we have a pair of aces. And so we ended up with both hands significantly better than what we started with. And then that's typical of performance for this resource trading network. And then once the cards have moved, they report back that they've moved to their new hands, and the system is back in a ready state where we're now ready for additional commands. So we've sent now and used the back-end system in order to execute the device twins. All we have to do is then say we want the twins to move locations, and then they send the information back. And a couple of the components of this architecture is that it's robust against interruptions in communications. The device twin on the server stays in its desired state until it gets a reported change back from the devices. And so if the device goes offline or the network communications are interrupted for some reason, when they're reestablished, the device twin will report back in its current state, and then the server will note that that's not the state that it's desired, and will send the desired command back to the device, and the device then will execute the change. And the desired state will stay in that state on the server until the device reports a completed change. The other component of this architecture is that it's secure. Each device has its own unique connection key with the server, and the only way it can talk back and forth from the server and the device is if that key is known. This means that on the setup side, that each device will have a manual step where the user inputs the key. That can be automated or distributed depending on how the devices get set up. So in summary, we started with a network of objects that might or might not be in an optimal configuration, and we thought if we could only trade those, that we might be able to do better and better allocate our fixed set of resources. And what we've done is attached an IoT connected device, an IoT device, to each one of our objects. Now that we've done that, we can all talk back with the Azure IoT Hub and optimize the resource allocation in this fixed network. Thank you, and if you have further questions or comment or conversations, please look me up on LinkedIn and we can talk there.